Okay, so I'm gonna try to finish up where we left off, which now we're retrieving the counters every frame, and now the task is basically recording these counters and then have some way of displaying them. So let's get to that. Give me a second. Okay. So what I'm thinking is we create a new structure for profile results with name and the time elapsed, or I guess in this case with milliseconds elapsed. Profile results and result count. Okay. So essentially, what we're trying to do is that we're caching. What the fuck? Okay, sorry about that. Now basically every time the session is recorded, they begin and end counter, and we're gonna say record results, I guess. Result count is going to be equal to session count. Profile result. So we kind of need to be careful here because we need another string duplication here. And obviously now, before we record results, we don't want to override it. We might have allocated memory for strings from our last result, so now we need to clear that. And if there wasn't any result from last frame, then result count is default to 0, and therefore this wouldn't get run. And lastly, we're trying to reset the what the hell? All right. Then in order to reset the profiler, I need to look at what resources have been allocated for the profiler. Okay, so basically we reset the current query index. Actually, before that, we need to free all the strings we've allocated for the sessions. Session index. So just to be certain, let's step through the code. I mean, this probably isn't going to work, but let's just step through the code so we better understand what's going on. Okay, nothing changes. The first frame should be nothing, and the next frame 20 read range. All of these look fine. And let's look at the frame data's internal variables. Query counter, counter buffer, result count. So we don't have any result count right now, so this probably skipped. Sessions, these names are all allocated memory that we need to free. So this should take care of that. But before we free it, we need to duplicate those into our result array that gets used to display the results. So say results. Cool. That all works. Session. Now it's time to free these strings that we allocated, and reset the current index and reset the current session index, which is pretty much everything we had. Now we're just resetting them. This is for the other frame data for back buffer 1. Okay. Okay, so this is working as intended. Still got our tunnel sync running just fine. Bit of boiling, but that's okay. Diagnostic tool shows memories. We shouldn't be having any memory leaks. Cool. Now I guess we're on to how we want to display this profile numbers. So I guess the simplest way to do this will be using printf. I really don't feel like doing another round of text rendering shenanigans. So if we just do that, this wouldn't actually print anything, and the reason is we don't see a command prompt, really. This is telling the compiler that we're building this as a Windows application instead of a, I don't know what you call it, a command prompt application. It's just that it has two modes in it. One is it spawns a command prompt for the application of one where it doesn't. So we want to switch to the one that does. What we need is just, well, guess what? The good old main, entry function. Of course, we don't get the instance that we used to have from the argument that gets passed in, but that's fine because get modular handle. This Windows function should give us the instance anyways. So this should be I remember this being the function, but now I'm not sure. Let's just try this. Okay. So now I'm expecting to see a command prompt showing. Yes. There it is. Hello world. Okay. So it seems like everything's still in order. Except now we have... What the fuck? Except now we have a command prompt. Not sure where those printfs are coming from. Oh, I remember. It's from track code files. It's when I was copying some code online to get us working. And now it should not have any of that. Yeah, it's just the hello world. So actually, if we're doing printf, we don't even really need the persistent data tracking for our profile results, right? All we need to do is go to engine. Don't really need the results anymore. So all we have to do is get rid of this. All we really have to do, what? Cannot open include file SDF engine, no such file directory. That's interesting because the file is right here. What the fuck are you smoking, compiler? Core results. Okay, we could just replace this with the sessions, right? Let's do a printf. Got milliseconds, and we have the name inside our session. So we can just do this. Okay. Let's run it. Yep, this gives us what we expect. Too bad when we actually close it, the command prompt goes away as well. Maybe... Is there a way to do printf that's not... So I guess it can't really... Let me just put a git char at the end so that when the application exits, we can still get a peek of the command prompt outputs. All right. So that's pretty much what we're looking at here. So path tracing, it's about 31 milliseconds, and it probably just the first frame, 146. I'm guessing that's the dynamic frequency scaling for the CPU, so not the CPU but the GPU. So basically what happens is that GPU at rest, the clock frequency is tuned to be very low to save power, and the first frame usually you don't get a lot of mileage out of GPUs because their clock frequency is still very low. It's still in the process of rising up this clock frequency to peak. But after the first frame, you can see now the speed of the path tracing went up to about 30-ish. So that's what we want. This get chart is not my favorite. Not my favorite way to get profile results, but I mean it works. So we got what we want, and you know, profile numbers is not an essential feature I want in this application. So that wraps up the profiling. So now path tracing is our main bottleneck. It's about 33 milliseconds. It's a long time. So if we look at the internal logic, pretty much nothing can be tweaked. I mean, it's just a unidirectional path tracing. Nothing too special here. The real cost is raymarch. Now this operation there's no memory load at all here. Raymarch is just purely a bunch of ALU instructions. So all we can do here is pretty much simplifying the either by reducing the number of instructions or simplifying the algorithm. I mean, simplifying as for the GPU. So from GPU's point of view, it's more simplified, but to us, it's probably going to be more complicated. So let me just try to change the. Let me pull this out to like a. Constant numbers. This will be T epsilon max iter. Get rid of our magic numbers and see if it still runs. For 256 and a T epsilon of 0.01. Let's see how much that affects the raymarch runtime. I think it's a little bit faster now. 22 milliseconds, not bad. Visually, I don't really see much of a difference, so I might just stick to this configuration. Is the light leaking through these holes? Anyways. So we might not be getting sufficient precision if we have these as our constants. I really like the soft shadow here. It's really nice. I guess one thing I forgot about was when we tried having some skylight, there was issue with the fog. So if I can jog your memory a little bit, if we have an environment light of say some degree of blue sky, the fog is attenuating the radiance into 0, and that is not blending well with the sky. So instead, what I should have done was have this be lerping towards the sky color. But do I have access to ray direction? Yes, I do. Am I getting the ray direction anywhere? Let me just hoist the ray direction up to here, and now radiance will be a lerp between let's hoist this out as well. Since this gets executed for both branches. Now this should be good, except I messed up the order. Yep. This is better. But I feel like the fog might be a little too strong, I think. Whoa, that's like volumetric. Cool. It's too far. Okay, maybe that's reasonable. That's too far. This is a linear attenuation. I want to have a sharper cutoff when it's farther away. So let me try tuning this number. I guess I can tune this outside of the clamp, which is safer. 2.0, if I do this, this should give us a nicer fall off. No, it's even worse. There we go, that's much better. And 100 units might even be too far for this one. So 50, that 80. Okay, 80 seems to be good. But I think that's too much skylight. Not this much. Still looks kind of bad. I guess I'm just gonna have no skylight at all, like before, but at least this fixes the issue we were having. $21. milliseconds. Now, one thing is, you might have seen my to-do list. It's this thing called enhanced sphere tracing. So one trick that they have proposed is, instead of stepping by the amount of biggest unbounding volume when you do sphere tracing, instead you relax the restriction a little bit. Say, dude, I know like it's only going to be completely safe if I step by this distance, but let me just step a little farther, maybe step twice that distance, and and then check if the extra step that I took has gotten me into some kind of inside some kind of surface. Now, this is not actually completely trivial to test, but they've come up with an algorithm that, given the distance that you query from your last step point and the current step point, you can actually figure out if that has happened or not. So let me actually do some reading, because it's been a while since I've used this. So basically, illustration of the classic sphere tracing. With the over-relaxation method, you can see it takes a lot fewer iterations to get to the point where it's gotten to. Hopefully implementing that will give us a big boost in our path tracing. So this is the clever bit, right? It's their criterion for detecting any overshooting. So let's try and implement that. This is our current raymarch loop. It's quite simple. I can put in a constant. Raymarch relaxation, I guess. So let's see how we want to do this. Screen space based intersection. That's something I didn't know about. Interesting. if they overlap. So if it's less or equal to prep step size, then we know we're safe. If it's the other way, we say is relaxed with a false, and we even have to kind of backtrack prep step. No, it's bigger. Yeah, when it's smaller. Okay, when it's smaller, that means it doesn't intersect. So that's a case we actually want to check for. All right. Let's see if this works. Chances are it doesn't. Undeclared variable prep step size. Okay, I meant prep step. Scale. That actually makes it more expensive, but probably not doing the right thing here. Scale, raymarch, relaxation. So upon initialization, qdist is some positive value, prep dist is 0. It's less or equal to prep step, which was 0, and that's async possible. Scale step t plus step. Comes back. If qdist plus prep dist. So this will be the sum of the two radius. This will be the sum of the radius of the two unbounding spheres. And as long as this is bigger or equal to the previous step, that means the two unbounding spheres intersect. If this is true, then that means it doesn't intersect, and we fall back to non-relaxed mode. I am not sure why it doesn't work. Let me run this one more time. And for some reason it's slower, which is interesting. prep this prep step. I mean, it somewhat works. Never mind. It doesn't even. Oh boy. Let's see. Let's see if I missed anything in the paper. I already have dynamic step size. So this artifact could be what we're seeing, I suppose. Let me try a less aggressive relaxation constant. You know, first of all, I mean, regardless of whether or not the algorithm works, I don't understand why it's slower. Because for sure we're stepping a lot faster now, right? And if we don't, we just say we never fail. We never check if we overstep. So we always try to overstep. This should give us better performance with broken images. And that's what it does. Let me see how fast this is. 20. That's marginal at best. 0.6. So now I don't even know if this optimization is worth it. 16, 14. Okay, that's a lot better. I guess we want to stick with 1 point. Is this overstep? So absolute value. Okay, this might be what I've been missing. I forgot that it's possible for the sign distance to be negative. And that doesn't fix it. Obviously it wouldn't. How could it be so easy? Ah, okay. Oh man, I see what's happening. Now the problem is, okay, we step back at this point, but the point query which we've calculated is still inside the overstep region, so we also need to backtrack this point curve as well. Alright, so that should be fine. Or not. I'm betting it doesn't work. Because nothing works. It actually works. How good is the performance? That's 25. That is quite a lot better than what we had before. So 25, I believe before had like 38 or something, 34 to 38. Now we're in the 25 region. So I would say that's a successful optimization that we did. Now we really try to push it 1.9. Might start seeing some artifacts, but this should be the best case for performance. No, maybe not. Maybe bigger isn't better. Okay, so actually I can just hold the window bar and it just stops, so I don't even have to get charged to pause the application when I close it. Okay, so this is nice. We've got a pretty decent speed up from our raymarch loop optimization. Now, I don't really think of any of the... So maybe path tracing is something we want to look at, particularly the divergent behavior. We could possibly do something with that. So okay, here's what I'm thinking. Okay, probably not enough time to get to it, but what I'm thinking is basically this. So first I want to kind of plot. Okay, guess what I'm trying to say is, so GPUs execute shaders in waves in lockstep, and in a divergent workload such as path tracing, there are going to be threats in your wave that, you know, in the middle of the path, it hits the ray misses something and the path is complete, because then it just starts sampling the skylight and that's it. You won't do any more bounces on those lanes. So eventually, after you've done some bounces, you're gonna have a lot of empty holes in your waves, and I'm thinking that could be we can sort of improve that by sorting the rays in similar directions, or doing some sort of compaction, so that we're not wasting a lot of the lanes in these waves. Yeah, I'm just thinking this is not going to be easy, but we did get a lot of mileage out of the enhanced raymarch day, so that was about, we shaved off about 13 milliseconds on a relatively weak GPU. So this is 1660, and now remember we're doing full path tracing of this SDF. It's kind of expected for this to be really slow, but it isn't that slow. What the hell? It isn't that slow actually, which is surprising. Well, I guess that's enough work for today. I'm gonna get off now. So yeah, good progress.